Hello guys, today we are going to start a new lesson with you, which means that we will introduce the artificial intelligence in order to what? In order to build some creative programs or another else, okay? And so this lesson is consists of the artificial intelligence and its application related to machine learning, deep learning, or any other algorithm can be learned or taught by us or the computer or itself. Okay. And so I give the heading in here like this one: Introduction to AI. Okay. And so firstly, in order to define the problem, we give some specific statements in here, like this one, problem statements. Okay. Suppose that we have some kind of function like this one. Suppose that we have the y is equal to the 2 times x. Okay. And so in each parameter in here, the x, for example, the price for oil, okay? And so the 2 is the how many liter are taken from us, okay? And the y is the total output or the total price, okay? This is the standard simple model, but in this case we can easily calculate all the prices that we need to pay in here, like this one, okay? Because we have the model in here with the term of the 2, and so the input variable x is equal to the what? The y. Y is equal to 2 times x. And so we can easily create some graphical depiction like this one: x, y, okay? And then, for example, if we have the 5 liters, and so the gas price is equal to the what? 10, okay? And so in here, the x is our feature or the input set, because we can determine all the features or all the prices by looking with the x value. And so the y is the output or the total price of our the oils, okay? And then we can easily set that this creates a simple model, okay? This creates a simple model. But the important thing is that we can understand that, okay? This is important because everything is given. In this case, we have it. We know it. 2, x, or the something else, okay? But what if we have the data or some graphical depiction in here, like this one? For example, if we have the x value in here as a feature, this is the output, and so if we have like this data or distribution for a given x, and so if we have this kind of system, and then we can assume that maybe our system is looking for the a times x squared plus b times x plus c. This maybe is the R feature, okay, or the model. But the graph is entirely dependent on the A or B or C parameters, because if for a given every x, and so if we know the A, B, C, and then we can produce the y value or the output value, okay? And so normally we have this form. But what if we don't know any model or A, B, C? This is the identical term because A, B, and C is equal to the R model. Okay? For example, if we have some kind of data in here like this one, and so how can we create a formulation to represent the relation between X and Y? How can we do that? This is a simple question, but the solution is simple. If we have known the exact equation, or if we have some specific variable in here, like this one. For example, for every X we have Y, and then we propose some basic function in here, like this one. We propose a or an equation like the Y is equal to the A times X squared bx plus c. Okay, and then we can put into every X data into Y. For example, we have the 0 value in here for the A times 0 square plus B times 0 plus C. Okay, and so for the X is equal to 0 and Y is equal to the 0. Okay, from the graph, for example, if we have 5 in here but the X is 1, B times 1 and C, and for example 101 A times X, for example 5.2 times B times 5.2 plus C. Okay, and it goes on. But in order to solve this equation, we can create the Y vector in here like this one, and A vector and bigger A with the including the A, B and C parameters in here like this one, and so we can give the X values in here. Okay, and so if we get the inverse value of the A minus 1 Y, and then we get the relation of the X to Y and Y to X. But there's some arising problem in here because we should give the X and Y value with the exact match, and so this is the exact solution with a specific point. But however, in real life we don't have an exact match, only the approximation of these results. And so how can we approximate the most likely solution in here? Because in real life we have noise or some other parameters, and we don't know the exact formulation of this graph. These graphs may be not represented by this formulation, but we don't know the model. Only we have the data and the parameters forms. Okay, and so how can we do that? In order to do that, we need to review the least action theorem. Or rule in physics. Okay, because it's important. In physics, we have an excellent notion about the nature, because in which the nature always seeks the minimum energy states. Okay, nature seeks always minimum energy states, or least action, minimum action. And so the nature always finds out the most efficient way from one point to another one, and we call it the least action, or the nature is lazy, which means that it doesn't like to convert energy from the potential to kinetic or otherwise. Okay, and then we need to give some another problem formulation in here. Okay, the problem is that we have some points or some mass in here. Suppose that we have the one point in here, the another point in here with the position of Q1 and Q2, and then we need to move the Q1 to Q2. But what is the best, or what is the efficient way to do that? For example, if we have this Q1 and Q2 in the coordinate system, and we can go this way or goes this way, but in one way is the most efficient way, and nature always find out this way in order to what? In order to complete these tasks. Okay, and so we need to formulate this like this one if we have this notion. And so in physics we have the for particles we have the kinetic energy and potential energy, and so we can define that if we have any Lagrangian in here, or the total energy formation in here, T kinetic and U potential, the kinetic energy is transformed into the U. Okay, and so if we have the high potential, and then we can go to the with the high kinetic energy, but at the same time cannot be both, because if we have the total potential and so we don't have any kinetic energy, or we have the total kinetic energy or the highest kinetic energy, we'll have the lowest potential energy in here. And so how can we formulate this notion? We propose a solution in here like this one, the solution. Okay, and if the nature seeks least action or minimum energy instead, or the efficient way, and so we can define is as S, and then we can write it down as Q. S is an action, Q is a position, and so we have the timeline in here T0 to T1, and so the Lagrangian is equal to the Q dot and T dt. And so if we have any formula which is given to minimize this energy, and so we can reach the behavior of the nature. Okay, so now assume that the efficient position or action is equal to Qt. Okay, which is the best path for a particle to vary from the Q1 to Q2. Okay, and so if I put the Q the bigger q into the smallest q, and then this function is minimized. Okay? And so, if there is any increase or decrease upon the qt, the bigger qt, and then this path cannot be smallest one or the efficient one, like this one, delta t. Okay? And so, this could not be the best path. Okay? And so, putting this formula into the equation, and then we have the SQ is equal to what? T0, T1, and LQ plus delta, Q dot plus delta dot, and T dt. Okay? And so, this is the what? The not the best path for our application. And so, in order to analyze this, we can utilize the Taylor expansion formula. Okay? Taylor expansion. Because we have in the Taylor expansion form the first derivative of the dynamics of this path. Because we have the kinetic energy and potential energy, and so the position position means that the potential and the dynamics is directly related to what? The first derivative of this q. Okay? And so, if we rewrite the SQ in here, like this one, T0, T1, and so we have the new Lagrangian in here, Q dot T, plus dl dq times delta plus dl dq dot delta dot and blah blah blah. And so this is the higher order terms in here. Okay? And so this can be considered to 0 because we have the first dynamics of these terms. This is an error, but in mathematical way or in physical way we don't have any meaningless situation. Okay? And so if we have the best formulation or the best path in here, like this one, and this is the minimum path or best path, and so these delta terms should be equal to 0. Otherwise we are wrong. The proposition is wrong. Okay? And so, how can we destroy these terms in here in order to prove our theorems? Firstly, we need to keep the delta form because it's our position. Okay? In order to prove that, we need to eliminate these terms because it's directly related to what? The delta dot. And so this must be goes to the 0. But how can we remove this term from this formulation? Or how can we write the whole equation depending on the entirety of the what? The position or delta or deflection rate. Okay? And so we can use the calculus formulation in here like this one, d dt and dl over dq dot times delta, and so this can be written like this one, dl dq dot times delta plus dl dq dot times delta dot. Okay, this is the calculus formulation of the what? The integral operation or the chain rule in the integral operation. And so this term can be rewritten as the like what? The dq dot times delta dot is equal to what? D dt dl dq dot times delta minus d dt dl dq dot times delta. Okay? And so if we putting into the what? Into this equation in here like this one, and so we will get the generic representation for our SQ. Okay? And SQ is equal to the what? The S bigger Q. This is the best pathway, and its energy. And so we have the integral term in here like this one, and so the L dq times delta minus d dt times dl dq times delta minus d dt times dl dq times delta and dt. Okay, so in this form we have the one term is coming from the Taylor expansion, the other term is the what manipulation of the other terms in here in terms of the delta operation, but we have also this term in here. This is the end point theorem in the calculus. This must be get the 0. It's the basics of the calculus, and then we can say that this is the best path and this is the delta path, delta s, and so this could be equal to the what? 0. And so we have this formulation in here like this one. Delta s is equal to what? T0, T1, and dl dq minus d dt dl dq dot times delta dt. Okay, and so delta cannot be 0 because it's equal to 0 and there is no kinetic energy or any deviation. And so if this term, we can utilize these terms, and delta s must be equal to 0, and so this must be equal to 0. And so in final theorems we have dl dq minus d dt times dl dq dot is equal to 0. And so this is the standard definition of the what? The Euler-Lagrange equation for an energy forms. Okay, and so this is the standard representation of the energy formulation for a given variables or the features. Okay, and then if we want to use this formula, and then we can obtain the dynamics of the systems. For example, in system dynamics we can write the Newton's law or the robotic arm manipulator dynamics or manipulations. Okay, and then if the dynamics related to the universe are directly derived from the minimization problem, and so we can define any other dynamics using our own cost functions, right? Because if the nature seeks always minimum, and then we can write the dynamics of the system. And so if we know these things, or the dynamics is a result of the what? The minimization problem, and so we can utilize this notion, minimization rule, for obtaining or to obtain the model or dynamics of the system. And so what's concerned about the model or dynamics in artificial intelligence? If we have this notion in here like this one, and so we can write another problem formulation in here. Okay, suppose that if we have any graph in here like this one, x and y, and so we have data in here, how can we utilize or how can find the generic representation of this formulation with a simple or the smallest error in here? And so like the nature, we can define a minimization problem. Okay? If the data are available in here, and we can say that there is a model or dynamics in here, and so we have a model in here, whatever if we don't know or not. Okay, and if there is a dynamics or the model, it should be a result of the some minimization problem, and so this model resulted of minimization problem because the nature it does. Okay. And so if the minimization problem can be constructed in here, and then we can find the model or even learn from any data in here, or which means that learning rules can be included at this time. Okay, as a result we can summarize all the things in here like this one. As a result, every dynamics or the model generate data or measurement in universe. Okay, every model produces data or measurement in universe. Okay, and so the dynamics or the actions determined this data. Action are responsible for this generation. Okay, and then we can say that in order to create dynamic formulation, the minimum principle can be used in here. Minimum principle can be or can reveal this dynamics, because in the first place we have reached the Euler-Lagrange formulation by minimizing the simplest function. Okay, but if there is no information about the model, we can use the minimization of energy that we can define, or we can define some cost function with the error term, like the E is equal to Y and Y real. Okay, and so this Y is directly from the what our model results. And so if we have this information in here, and the kinetic energy and potential energy are stored in the universe, but we can change the energy type. The energy type is that our model results minus Y real, or real data coming from the universe or the measurements. Okay, and this E can be representable in this form, and so it's consistent with the universe dynamics or the behavior or the features. Okay, and therefore if we have any data in mathematical formulation, and we can define the energy function and minimize it to find out the correct model, and we can reach correct model using this principle. Okay, and so if the energy form is in the mathematical notation, we can learn from data using energy function, and so we can build general math formulation based on data and the minimization rule. Okay, and so this unknown pattern modeled by mathematical formation of the standard function is called the learning. In here 8, the learning is about how can we act in this system, but in the mathematical formulation we have the derivative terms or the dynamics terms is included in the learning process, and this whole creates the artificial intelligence definition. Okay, so in the standard definition of the AI, we have the definition like the branch of the computer science developing algorithms capable of performing tasks that require human intelligence, like the minimization principle. Because if you don't have any model in here, and then we cannot use this model. But if we have the energy function, and if we minimize it, like the Euler-Lagrange equation, and then we can reach the model pattern. Okay. And so the standard definition of AI also includes the task that includes the learn from experience, recognition, the pattern, understand the natural language, and make a decision, like this minimization principle from the learning process. And so we can simulate the cognitive function of the human using the AI. But how we can simulate the cognitive function of the human? We can use these formulas in the mathematical notation, and we can build the model. And so we propose any function to be minimized from the learning process. This is called the AI function. Okay, and so this is the end of the lesson. I hope you have learned about the introduction of the AI course in here. In the next session, we will talk about the types of the machine learning and machine learning algorithms. Okay.